Good evening, everybody. So we are moving on to the next session, and welcome, Vinti, to the strategy class, and it's over to you.
Sorry. Good evening, everybody. So today I understand I need to end by 8 o'clock. Okay, I think you have another class after this.
Yes, ma'am, another subject.
Okay. So Shripriya, I just mailed you one research paper. Okay. I will show it on my desktop. Okay. But you can send it to the participants. It's a very simple paper. Uh, So when I read the feedback, I think some of the feedback was related to in terms of how can it be customized to palliative care. Okay, so I think that was the biggest concern. But statistics is statistics in the sense is that I mean some of the examples we can give with medical literature, but finding specific examples with relate to palliative care, it becomes a little difficult. Um, most of the research papers are at a little higher level. So they may have used ANOVA, they may have used logistic regression, some of them have used simple regression. Okay, so we haven't got there till yet. We are still going step by step, right? So today we hope to cover three kinds of distributions. One is binomial, the second is Poisson, and the third is standard normal distribution, which is quite a bit used in hypothesis testing. Okay, so once you start understanding distributions, and then we go to once we go into this, once we finish this, then the next time we can start with hypothesis testing. So today we'll use calculators. You don't have to calculate anything, right? As long as you understand the subject, right? We have online calculators, so nobody really has to learn the formula or anything of that sort. It's okay if you can just understand the concept and use the calculators to calculate. So that is more than enough. Okay, so I'm just going to show you one particular paper which I have. Okay, uh, just let me share my screen. Okay, can you see this paper? Everybody can see this?
Yes.
Okay, so this is a very simple paper that I found. Okay, it's actually written in the context of you know India. Okay, it's written by Manipal Hospital. So it's study of nurses' knowledge about palliative care. It's a quantitative cross-sectional study. Okay, now I'll just go through the methods and stuff. Okay, we haven't done ANOVA, but we will discuss that later. Okay, so basically, in terms of the context, it was that nurses and other healthcare professionals are inadequately prepared to care for patients in the palliative care. So they wanted to assess the knowledge about palliative care among nursing professionals using the palliative care knowledge test. So there is obviously some palliative care knowledge test, and they did a cross-sectional survey of 363 nurses in a multi-speciality hospital. It's used a self-report questionnaire, okay, which is obviously developed by uh, a medical professional, and it has 20 items about palliative care. About each of the persons has to correct, incorrect, or unsure. Okay, now within that score, okay, within that scale, within that questionnaire survey, it has 5 subscales. Okay, so it had philosophy had 2 items, pain had 6 items, dyspnea had 4 items, cited problems had 4 items, and gastrointestinal problems had 4 items. Okay, now the reason why I am doing this paper is last time we had done something on central tendency. So I'm basically trying to tell you, how measures of central tendency have been used in this particular paper so that you can relate to what I've done. Okay. Now, if you look at this, the overall total score of PCKT was 7.16. plus minus 2.69. Okay, so obviously this means what, right? It means the standard deviation. Okay, right? So it's basically 7.16 plus minus 2.69. Okay, this philosophy score was 73 plus minus 6.65. Okay, pain score was 2.09 plus minus, which is the standard deviation. Okay, and dyspnea score was 1.13 plus minus 0.95. Okay, and similarly for the others. Okay, then the female nurses scored higher than their male counterparts, but the difference was not significant. So they would have calculated the scores, okay, the female scores, the female nurses and the male nurses, and they would have, subjected to a test wherein they would have said that, okay, whether the difference between the two scores is there a significant difference between the two. So when we do hypothesis testing, we will get on to that significance testing. Okay, so that's my next class. Okay, but today we'll understand normal distribution, so you'll understand why this is important. Okay, so I won't get into anything else. Okay, I am just going through some of the descriptive knowledge. Okay, so you can see out there, this is overall descriptive study of study participants. Okay, so they have written what is the age, total sample size is n. Okay, age is on an average is 24.31 plus minus 2.47. Okay, that is the standard deviation. So they have put the, it is in brackets. Okay, they have put the, it is in brackets. Okay, so you see all values are in number. Okay, values are in mean and standard deviation. Okay, right? So here, in where it is in percentage, it says all values are in number n percentage. Okay, so male 40. Okay, but the percentage of males was 11% and the female was 89%. Never married. Okay, 315 was the sample. 86.8 was never married. 12.9 married. Widowed was 0.3%. So this is how they have described. Okay, and if you go to palliative care knowledge total score, okay, so you will find 7.16 plus minus 2.69. That 2.69 is the standard deviation. Okay, okay, so I am, and here they have graphed it. Okay, they have graphed it. Okay, so these are the number of items. Okay, and they have graphed it in terms of unsure how much percentage, incorrect how much percentage, and correct. So they have, whatever the scores was, they took a percentage distribution. Okay, and that's how they graphed it. Okay, then they have also kind of described, they have done a division between the male and female. So taken an average of the pain scores, what they understood in terms of this item between the male and male. And you can see there is very little difference between the male and female. There is difference. Okay, females are slightly more, but the difference is very insignificant. Not too much of difference. Okay. Right. Then they have looked at scores. Okay. Now this is in terms of total scores. Okay, and then they've divided among inpatient ward, ICU, outpatient unit, and others. Okay, so this is again depending on what nurses were wherever they were stationed. Okay, there, and then they've also looked at it in terms of subscales. That is philosophy. Again, the nurses might have been stationed across different units. So they wanted to see whether a particular nurse stationed in something would be knowing more or not. So it seems that the outpatient unit nurses seems to have a larger score than the rest of them. Okay, the ones in the inpatient work and the ICU and the others, right? So this is what it pretty much it is. So this is just a demonstration in terms of how you are going to use descriptive knowledge. Okay, so everybody is, I've sent the paper, so I'd request Shripriya to kind of send the paper to you, and then they've also done some correlation of the total scores and the with age, present work experience, and total work experience. Okay, so this is one paper which was relatively simple and used descriptive statistics. okay, and is fairly relatable in other respects. Right? Any questions, everybody? Anybody? Anybody has anything to say?
No. No, ma'am.
Everybody good? Today nobody seems to be happy about attending a class. Everybody is tired. Seems like, ho gaya 4 5 weeks, too tired, right? We need a break. It's like this kind of a feeling that I'm getting.
No, ma'am. We are still motivated to learn more.
Okay, good. So I'm trying to, take it gently, try and relate it as much. I'm not a medical professional, but I try that, statistics is sector agnostic. It depends on us how we are going to use it. Okay, so the application is always in your hands, but so we try and pick out papers and stuff. So over a period of time, you kind of get used to consuming different levels of papers, and you will be able to relate whatever you learned in class to the paper. It will not happen in a day, it will happen over a period of time. Okay, so don't worry, we'll take it gradually, but it will eventually, it will happen. Okay, so I am just going to share my screen on the presentation now. Okay, so today we'll do some calculations. Okay, okay. So last time we had done something about specificity and let me just go to this. Yeah. Okay. So we had discussed something about sensitivity and specificity of a test. Okay. And then we had gone into an example. Okay. Uh, this is a particular example. Okay. So for example, okay, we had done this example. A medical research team wished to evaluate a proposed screening test for Alzheimer's. The test was given to a random sample of 450 patients with Alzheimer's disease and an independent sample patient of 500 patients. So total we had a 900 sample, 450 we had Alzheimer's and 500 we did not have Alzheimer's. Okay. And all these populations, because you need to compare, okay, you need to only compare apples to apples and oranges to oranges. So all these subjects were 65 years and older. Okay, so we wanted to calculate the sensitivity of the test and specificity of the test, right? So sensitivity of the test is obviously positive, okay, and the total number who had Alzheimer diagnosis, that's 436 upon 450. And if you want to look at specificity, is that the person did not have Alzheimer's diagnosis and the test was also negative, right? So that in this case was 495 upon 500. Okay, so you were able to calculate the specificity of the test. Okay, now I will, for the timing, I will leave out this. Okay, the positive probability of the test. Let's go on to the next, because I think this will take a little time to consume, so we'll go on to the next. Okay, now this is a distribution. Okay, now this is a typical normal distribution that is happening out here. Okay, this is a normal distribution. Now if you can see, okay, your mean is the same. Okay, if you look at this distribution, you will find that the mean is the same, but the spread of the distribution is very different. Okay, so your standard deviation in the first case is sigma 1, and the standard deviation of the second population is sigma 2. Okay, this is a distribution with separate spread, but because it is a normal distribution, the left hand side of, if you look at the line in between, it divides the total area into two parts. Okay, now this is where we use, this is something called a standard normal distribution, and it is usually used for variables which have a continuous distribution, okay, which are continuous variables, okay, those are where we are using continuous distribution and where we use a standard normal distribution, okay. So for the timing, I've just shown you. I'm going to go to other sets of distributions, okay, where I am going to talk about a discrete distribution. And in this discrete distribution, there are two distributions which are very popular. One is called a binomial distribution, okay, and one is called a Poisson distribution. Now both are extensively used in medical sciences, okay. So and I will give you examples from medical sciences. I've given some numerical stuff, okay. Always remember that the total sum of the probability in whatever case will always be equal to 1, okay. Now what it does say is the probability distribution in a discrete random process has a countable number of possible values, whereas a continuous random variable takes all values in an interval of numbers, okay. So this is the basic difference between a discrete random variable and a continuous random variable. Now in a probability distribution of a discrete random variable, what does it say? Is a table, graph, formula or other device used to specify all possible values of a discrete random variable along with their respective probabilities, okay. So this will become a little clear, okay, but all we are saying is that the total value of a probability can never be equal to more than 1, okay. Now here I am just going to sort of explain to you how this distribution thing works, okay. It's fairly simple. Now here I have this example which I have taken from a book, okay. Now it says that there are number of assistance programs utilized by families with children in Head Start programs in Southern Ohio, okay. So this is the number of programs. There are different types of assistance programs, okay, and we are looking at the number of people who have used those number of programs, okay. Now if I look at this bottom figure, it is 297, okay. Can everybody see my screen? Everybody can see my screen?
Yes, yes.
Okay. So if I divide 62 by 297, what do I get? Can anybody use a calculator on your mobile or something? If I divide 62 by 297, what do I get?
Point 208.
0.208.
8.
Yes. And if you can see on the other screen, you can see the frequency of this 0.2088. Can you see this? Table 4.2.2 probability distribution of programs utilized by families along the subjects. Okay. Now, essentially what I have done is I have converted a frequency table into a probability distribution, right? Because I have divided it by 297, right? The sum total of all of this is going to be equal to 1. Everybody okay with this? So if I divide 47 by 297, I will get 0.1582. If I divide 39 by 297, I will get 0.1313. If I divide 39 by 297, right, what will I get? Again 0.1313. If I divide 58 by 297, I will get 0.1953. And it's like the figures are given this. If you look at the graph next to it, what they have done is simply graph this probability. Okay, so you have the number of assistance programs and you can see one, right? You have a probability. Now this is what a probability distribution is looking like. Everybody okay with this?
Okay.
Fair enough? Clear?
Yeah.
Now in your let's say if I had to convert it into something that you would understand. So suppose you had many palliative care programs, okay, and you gave the choice of patients okay, in terms of, you know, what facility they would use. And if you made a table like this, you could actually draw this kind of a probability distribution. Does this make sense?
Okay, ma'am.
Right? So if you ask, or you had different kinds of patients who were doing palliative care and you had different facilities, so let's say you had, instead of number of programs, you had different palliative care facilities on the left hand side, and frequency would be the number of patients in each frequency, you could possibly convert that into a probability distribution. Okay, next. Okay, now what we are saying is that there are two essential properties of a probability distribution of a discrete variable. Number one, okay, that the maximum probability is less than equal to 1. Okay, the range of probability, it is between 0 and 1. Right? So you can have no probability less than equal to 0, and maximum probability is less than equal to 1. Right? So this is your range of probability. And for, let's say, for different this thing, the sum of all possible events is equal to be 1. Right? The summation is always probability of different values of x or values of situations or circumstances will always be equal to 1. Okay, this is the essential property of a probability distribution of a discrete variable. Okay, now let's say if I look at this sum, what is the probability that a randomly selected family used only 3 assistance programs? Okay, now let me go back. Okay, okay, so if I go back, 3 assistance programs is what? Can anybody tell me what is 3 assistance programs? What is the probability? Only 3 assistance programs. What would it be? Anybody wanting to take a guess? It should be 0.1313, right? When we say what is the probability of somebody using only 3 assistance programs, it would be 1.1313. Am I right or am I wrong? Is it clear to everybody?
Ma'am, is it the 13% you are saying?
Yeah, this is
13?
0.113%. Yeah, 0.1313. Can you see this? You
Yeah,
want me
ma'am.
to-
Yeah, ma'am.
let's
But
go to
when
the
we
question. Okay? It
when
says,
we report it in the percentage, we report it by like 13, maybe the
yeah,
13
if you can,
percentage.
yeah, 13.30. Yeah, if you want to do it in percentage, it will be 13.13%, right? Okay. Now, what is the next? What is the probability that a randomly selected family use either 1 or 2 programs? Okay, either 1 or 2 programs. Now, can somebody tell me the answer? What is the probability that any random person would use either 1 or 2 programs? What would it be? What would the answer be?
35%.
Yeah, it will be 35%. It is 0.2088 plus 0.1582. Right? It will be something like, if you calculate it, will be a little bit more than 35. Okay, it will be the sum total of these two numbers, 0.2088 plus 0.1582. What is that figure? 0.3670. That is, if you want to convert it into percentage, it will be 36.70. Okay, which is also accurate. Everybody good with this? Okay, let's go on to the next. Okay, now if I do a cumulative frequency table, okay, and a cumulative frequency table is, it's just the sum total of the frequency distributions. Okay, so for example, here in this case, okay, let me see if this is, if I have a value. Okay, So here in this case, if I make a cumulative frequency, it will be 0.2088 in the first. In the second, it will be against 2088 plus 0.1582. Third will be these two figures plus 0.1313. So this is a cumulative frequency table. And instead of looking like this table, it will end up looking like this. Right? So it is the summation of the frequencies, right? And the summation of the frequencies, as you can see, it is the maximum is going to be equal to 1. Okay. Now if I had a let's say a sum, okay, let me go into this. Let me just go to this. Okay, let me go to this. Okay. So we did this probability that a figure at random with 2 or fewer assistance programs. Okay. Now let us say, okay, what is the probability if I do a cumulative frequency table? What is the probability that a randomly selected family use fewer than 4 programs? Okay, so they're asking me what is the probability that a randomly selected family use fewer than 4 programs. Now if I go back to this table, what would the answer be? What it say? Randomly selected family would use less than 4 programs. What would it be? Anybody willing to take a guess? Fewer than 4 programs.
38.3. Sorry, 4.
Sum total of 0.2088 plus 0.1582 plus 0.1313. Are we good with this?
Yes, yes.
Okay. So this is how you use a cumulative frequency table of, of a discrete variable. Okay. Similarly, if it says, okay, what is the probability that a randomly selected family used 5 or more programs? Okay. So what I would do in this case, okay, since I know my probability is equal to 1, okay, now is use 5 or more programs. That means that person has not used 4 and less. So if I subtract the probability of 1 minus probability of sum total of up to 4, I would get my probability, because I know that the total probability can only be 1, okay, and less than 4 is equal to what? Less than equal to is this 0.2088, 0.1582 plus 0.1313 plus 0.1313. So if I add up this, it will come up to 0.6296. So I will get this probability. Okay. So this is a basic understanding of probability in case of a discrete probability this thing. And this is how you would, in your normal parlance is, let's say you have a lot of data and somebody comes and asks you, so what is the probability that somebody would select this kind of a program or this kind of a facility to, get palliative care? You can answer. Right? Or you can say that if you take a sample and you kind of do the statistics and do a sampling frame, okay, and let's say you collected a lot of statistics from districts, and you say on a random, if people, if I select, or if I take a sample of, let's say 10 people, right, how many will probably select this kind of a facility? Okay, so something like this, if I do this, I can actually do this calculation. Okay, now if I want to sort of calculate the mean and variance of a discrete probability distribution, now this is, I will send you the slides, don't worry about this, right? This is how you do it. In this case, as you can see, is if I want to calculate the mean, what I have done is multiplied the frequency, okay, the number of the program multiplied by the probability of that. Okay, so this is how I've done. So my average is 0.358. So you see 1 into 0.2088, 2 into 0.15823, 3 into 0.1313, and so on, because I had variables, right? So this is my average. 1 minus whatever is the average, square it and multiply it by the respective frequency, respective probability, I will get my variance is this. If I take a square root of this, I will get the standard deviation. Okay. So I am not doing the calculations because I don't want you to do the calculation. I am just kind of explaining the concept. Okay. Everybody good with this till now? Okay. Okay. Let me just, stop for a moment. Okay. 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 So does, before we get on to a, Bernoulli distribution, can you describe me a situation where you would denote something in a medical situation as a success and something as a failure?
Treatment option.
Treatment, okay. What else? So, any number, any particular situation, you can convert it into a Bernoulli distribution. Okay. It really depends on the way you look at, statistics. Okay. So let's say, you give palliative care to 100 people. Okay. Now, those who are happy with palliative care, it is a success. And those who are not happy with palliative care, you can say it is a failure. It is just a way of denoting an outcome, success and failure, right? Similarly, it is, um, you walk into a hospital. They say those who are satisfied with outpatient services, okay, right, success. Okay, those who are not satisfied with success, okay. You can also look at it in this way. You can also kind of do it. Okay, people walked in, you know for a checkup and got further tests done. Okay, so X number people walked in, okay, but a certain percentage went on to do some, investigative tests. Okay, that is a success. And those who did not, do it, that is a failure, right? And the possibility of success and the possibility of future. So if success is 0.5, the failure is also 0.5. If the success is 0.8, the failure is 0.2, right? Does this make sense? Right? Now, any number of situations can be modeled in a Bernoulli's case, right? As long as you understand that there are two possible outcomes. One is a success, you have to label as a success, and one you have to label as a failure. Okay, and this is a discrete distribution. Why? When I said that you are looking is what is the possibility of, if I look at 10 people, okay, how many people would, if I look at a sample of 10 people, how many of them would possibly, go for further investigative tests? Okay, so let's say that I have looked at data over a 100-day period and I have found the probability of people going in for a test is, let's say, 30%. Okay, and the probability of not, going in for a test is, let's say, 70%. Okay, now I say that on a particular day, let's say 50 patients came. Now I want to know what is the probability of exactly 30 people of those 50 people going in for further tests. Now, does this make sense? Is that a possible situation that you can think that you can relate to?
Vinti, you have not shared anything. You are just
I
speaking.
will just share it. I was just talking right now. I was just trying to first,
Okay.
sort of detail the possibility, and then I will share my presentation. Okay. Okay. Okay, so this is my presentation. Okay, it says a Bernoulli process. Okay, a sequence of Bernoulli trials forms a Bernoulli process under the following wide conditions. Each trial results on one of two possible mutual outcomes. One of the possible outcomes is denoted arbitrarily as a success, and the other is denoted as a failure. The probability of success denoted by P remains constant from trial to trial. Like it doesn't change, right? Over a period of time, okay, we say the probability of success remains constant, right? And the probability of a failure is denoted by Q, and obviously that will also remain a success. The trials are independent, which means that the outcome of any particular trial is not affected by the outcome of any other trial, and the probability of a trial does not change from observation to observation. This we've already said. Okay. Second, now let's look at this. Okay, I'll go very slowly on this. Okay, so for example, this is in terms of having a probability of having a full-term birth and a probability of not having a full-term birth. Okay, so for example, let's say all birth records for health statistics in a particular calendar year were looked at, and one found that 85.8% of the pregnancies had delivery in week 37 or later. Okay, now that is counted as if a woman delivers in the week 37, pregnant woman delivers in week 37 or later, that is counted as a success. And if she delivers less than 37 weeks, then that is counted as a failure. Now we are not saying that it is a failure as in something happened to the child, just because it was it is anything less than 37 weeks is risky, so therefore we have labeled that outcome as a failure. Okay, so as I said, it depends on how you are going to think through a problem. Okay, so P in this case was 0.858. Okay, and Q in this case will obviously be 1 minus 0.858, and that is 0.142. Okay, now let us assume, right, you have done 10 trials. Okay, you've done 10 trials. Okay, and you want to say, let's take a sample of, let's say, 5 sample. What is a random, let's say, right? What is the probability that a random sample of 5 drawn from a specified population of observing 3 successes? Okay, now let's say that when you say random sample of 5, and you may have done many trials. Okay, so you can happen, right, 5 patients walk in. Okay, so it can be success, 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 failure, failure, success, failure, failure, success, 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 failure, right? So you can see that these is the sequence of events that they can happen, right? So the combinations may differ. Okay, so in a binomial distribution, it is not just in terms of looking at the probability of success and failure, but it is also looking in terms of the number of sequences that are possible, right? So in this case, if you look at 5, okay, right, these are the possible sequences of how that in a sample of in a sample of 5, these are the possible ranges, ways in which that success and failure can happen. So there's a total of 10 ways that it can happen. Okay, so they did a calculation, and then they say, okay, it is a original question is, what is the probability in a random sample of size 5 drawn from the specified population of observing 3 successes, record of a full-term birth, and 2 failures, record of a premature birth? Okay, now in this case, because there are possibility 10 combinations that you can have, so in a binomial distribution, this is how you do it. 10 into, right, success is 3. Okay, so 0.85 P3 and Q2. Okay, and so your probability is 0.1276. Okay, now here in this case, we had a very limited sample, so therefore we could possibly draw these sequences and all. But in case we have a huge sample, it is definitely not possible to draw out these sequences that, okay, what is there? So therefore, we have something like this. We use something like permutations and combinations. Okay, so permutations, in this case, we are only looking at the combinations, right? We are not looking at the ordering. Okay, it doesn't matter to us how they are ordered. All we are saying that, for these outcomes to happen, there are 10 possible combinations that can happen. Okay, so if you look at this, if you look at the way combinations are done, the formula of a combination is, right, total number of a sample, okay, right, and factorial of that, right? So my total sample was 5, right? So factorial of 5 will be 5 into 4 into 3 into 2 into 1, okay, and in the denominator, and I'm only explaining you to the concept, you don't have to do the calculation ever. Okay, this is just to make you understand, you do not have to do the calculation. Divided by x factorial. Now x factorial just successes was 3. Okay, so it will be 3 into 2 into 1. N minus x is 5 minus 3. So that is 2. Factorial of 2 is 2 into 1. Okay, so this comes to 10, which is exactly the figure that we had in the earlier example. That is the 10 combinations that was possible. Okay, now let's look at an example. Okay, this is another example that we are looking. Let's say 14% of mothers admitted to smoking 1 or more cigarettes per day during pregnancy. Okay, if a random sample of size 10 is selected from this population, what is the probability that it will contain exactly 4 mothers who admitted to smoking during pregnancy? Okay, so what is my 14% is my success, that is P is 14, and therefore what is Q? 0.86. Okay, my sample is 10. Okay, so 6, 4 is my success. Okay, so N is 10, right? I am looking at 4. Okay, so 4 in this case is X, N is equal to 10. Okay, so therefore in terms of my combinations, it will be 10 C4 0.86, because Q is 0.86, so therefore 6, P is 0.14, and therefore 4. Okay, and then I do 10 factorial divided by n factorial divided by x factorial multiplied by factorial of n minus x. Okay, now I am going to put this calculator out here. Okay, I'm going to put it in the chat box. Okay, I am just going to use the chat box. This is a chat box. Okay, let's go to the chat box. Right, anybody can open this. Now this is, as I said, you don't have to do this. Everybody can see my screen. Can everybody see my screen?
Yes.
Okay.
Yeah.
So in this case, what is my probability? In this case, calculate. Now in this, what is my calculate P? Okay. So what is my probability in this case? What is P? It was 0.14. Right? What is N? 10. And what is number of events? 4. Right?
Yeah, 4.
4, right? And let's just calculate. Okay. So probability of exactly 4 events is 0.326. Of less than 4 events is 99.27. Of more than, so they've done all the calculation. If you want to do more than 4 also, 0.73. So they've done all kinds of combinations. Okay. Now let's make up something. Okay. I've given you the calculator. Okay. I want you to try it. Everybody has a calculator in the chat box. Okay.
Yes.
So let's construct a scenario. Okay. So let's say that 100 it was been found that for every 100 patients submit, that come into the oncology department, 20% need palliative care. Okay, so what is P in this case? What is P in this?
20.
0.20, right? And what is Q going to be? What is Q?
0.8.
0.8. Okay. Now I say that on any given day, okay, 20 patients come to an oncology department. Okay. What is the probability that exactly 6 of them will need palliative care? Okay. Can we use a calculator and do this calculation now? P is 0.20, Q is 0.8, and I have said that let's say 20 patients are there in our, what is the probability that at least 6 patients will need palliative care? So N is 20 and X is equal to 6. Now can we use a calculator? I don't know the answer. I have not used it.
And 20 or 100?
I estimated on 100. Okay, so that is why how I got my P is equal to 20. But I am saying on any given day, 20 patients walk in. What is the probability that exactly 6 patients will need palliative care? Okay, so my P was 0.8, 0.20, sorry. Okay, number of trials was 20. Okay, 6. Right? Can you see my, shall I share my screen? One second, let me see. Okay, is everybody can see the screen?
Yes.
Right? Okay. So exactly 6 events is happening is 0.10. Less than equal to 6 is 0.9133. Okay. Probability of greater than 6 is 0.08. Of less than 6 is 0.80. So they've given you all possible combinations. Everybody good with this?
Okay.
Easy enough?
I think we understood.
Everybody's got the same answer? Okay, everybody's done it? How do you feel?
It's simple.
Are you feeling good?
Yes, yes.
Less scared of numbers. Right? The fear of numbers has to go. Right? So in this case, right, looking at this example, you could, do a lot of calculations. It just depends how you are going to model a particular situation. Okay. Shall we go on for another 10 minutes? Or do you want me to stop? Or you want, let's have a kind of an, sharing, I can do Poisson distribution.
Yeah, you can go on.
Okay, let me just move on and let me try to do Poisson distribution. Okay, so this is where I've got this. Okay, so this is, let's assume, okay, I've taken an exam. It was found that all those who were obese, okay, 25% of them also suffered from hypertension. Okay, let us take an example of 10 obese people and find the probability of finding exactly 3 who were hypertensive. Okay, point tiger, 3 or more were hypertensive. Okay, 3 or more were hypertensive. Okay, so that is 3 or more. Okay, so you can, if it is 3 or more, okay, so you find out less than 3 and then subtract it from 1, right? So exactly, you say 3 or more, right? It means you look at the probability of 2 events, okay, and then you can, subtract it from there. Okay, fewer than 3 were hypertensive, right? So you can actually do this. Less than 3 is 0.77. Okay, probability of more than 3 is more than 3 is equal to 0.47, right? So all these combinations are possible. Okay, so now let's look at Poisson distribution. Now the next discrete distribution that we consider is a Poisson distribution named for the French mathematician Simeon Denis Poisson. Okay, and he, derivation in 1837. Okay, it has been used extensively as a probability model in biology and medicine. Okay, now here in this case, this is the formula of the Poisson distribution. Okay, now where would you use Poisson distribution? Okay, now if X is the number of occurrences of some random event in an interval of time or space or some volume of matter, the probability that X will occur is given by the Greek letter lambda, which is called the parameter of the distribution, and is the average number of occurrences of the random event in the interval of volume. So normally, right? So if you say that, if you look at, the incidence of adverse events, okay, because of a vaccination over a period of 4 months, so you found 12 adverse events in a period of 4, right? Exactly, it's 10 events. Okay, now that is something what is called a Poisson, would be resembling something like a Poisson distribution, right? Because it's not too many events, it is over an interval of time you found that, you found 10 adverse events. Okay, symbol E is a constant. Okay, it is measured by 2.7183, that is the value of this. Okay, now let's see. In the Poisson distribution, the occurrences of the events are independent. The occurrence of an event in an interval of space or time has no effect on the probability of the second occurrence of the event similarly like a binomial, right? Theoretically, an infinite number of occurrences must be possible in the interval. Okay, theoretically, it doesn't say it happens. Okay, the probability of the single occurrence of the event in an interval is proportional to the length of the interval, right? So if I'm having 10 adverse events in, let's say, 4 months, now if the number of the interval increases to 1 year, then the probability is going to be somewhat proportional to that. Okay, in an infinitesimally small portion of the interval, the probability of more than one occurrence of the event is negligible. Okay, now in a Poisson distribution, the mean and the variance are equal. Okay, so let's how to look at this. Okay, you can all see my screen, right? Everybody can see my screen?
Yeah.
Okay, now it says, in a study of a drug induced I don't know how to pronounce it, anaphylaxis among patients taking rocuronium bromide as part of the anesthesia. Okay, Lake and Rotterdam found that the occurrence of anaphylaxis followed a Poisson model with lambda is equal to 12 incidents per year in Norway. Find the probability that in the next year, among patients receiving rocuronium, exactly 3 will experience anaphylaxis. Okay, so here in this case, right, the model is, is X is equal to 3. Okay, and we find that, in that particular interval, lambda was equal to 12. Okay, and as I said, it is proportional to time. Okay, so in this case, the probability of 3 events is e to the power of minus 12, 12 to the power of 3 divided by 3 factorial, right? And the probability comes as 0.00177. Okay, now if I look at another similar, this calculation, okay, what is the probability that at least 3 patients in the next year will experience anaphylaxis if rorquonium is administered, right? So it says earlier it was only 3 patients. Now I am saying at least 3. So it can be 0 also, it can be 1 also, right? It can be 2 also. Okay, right? Sorry, at least 3 means that not, it won't be, it won't be 0, 1 and 2. Okay, so what they have done is that I have taken 1 minus, okay, we are saying that complement of 3, right? So it will be, there will be a situation where there will be no patient who will administer, 1 patient, 2 patients, and I have subtracted the probability of them. Okay, so if it says at least 3 patients, okay, so when I say 3 patients at least, that means I am subtracting the situation of that 0 will not happen, 1 will not happen, 2 will not happen. So 1 minus these 3 events and I will get my probability. Okay, again, you don't need to have calculation. As long as you understand the concept, the calculation will be taken care of, but you should be able to present it properly. Okay, and I will send you all these slides, not a problem. Okay, so if I look at this, there is also a calculator for this. Okay, I'm putting it in the chat box. Okay, so this is a Poisson calculator. Okay, everybody can see my screen. Everybody can see my screen.
Yes, yes.
Okay, so what was it in the last example? Okay, if I go to this particular example, okay, it says lambda was 12, right? And it says lambda was 12 and it says 3 will experience. Okay, so if I go to the calculator, yeah, okay, so rate of success is what? Okay, so this is my probability, exactly 3 occurrences. What is my x out here? This was 12. Okay, and what was my x out here? 3. Okay, lambda was 12. Okay, and I want exactly, I have these possible exactly these many occurrences. Okay, let me just calculate.
And if we are using the calculator, we cannot see the calculator now. We are
1
seeing
second.
the PowerPoint presentation.
Can you see my screen?
Yeah, we can see the PowerPoint presentation.
You can see the power, but let me just again, 1 second. Okay, can you see it now?
Yes.
Okay, so in this case, lambda is 12. I was looking at exactly 3. Okay, calculate. Right, I can always do, right, less than equal to 3. Okay, right? So, and in this calculator, they actually give you the entire calculation, right? Probability of at most 3 occurrences, so less than 3, so it is P0 plus P1 plus P2 plus 3. Okay, so they actually calculate all of this and then it comes out to this answer. Everybody can see? Okay, let's try an example. Okay, I'm going to stop share. let's look at a situation, and everybody can try it, and then I'll stop. Okay. Okay, can we look at adverse events or a negative reaction to a drug? Can we look at that particular example? So let's say that you gave, let's say for pain management, a certain amount of morphine. I don't know, I may be talking out of the thing, but just bear with me. Okay. And you had an adverse reaction of giving morphine. Okay. And over a period of, let's say 6 months, right, 10 adverse events happened. Okay. Now let's say you have 20 patients who are under your unit. Okay. What is the probability that you will have at least 2 who will suffer from an adverse reaction from morphine? Okay. So lambda in this case is 10. Okay. Now you had, total of, 20 patients. Okay. And you are saying that what is the probability that at least 2, okay, at least 2 will suffer an adverse reaction? Right? Please try the calculator. Is this the answer that you're getting? Everybody's got this answer? Okay. Everybody managed to use a calculator?
Yeah.
Okay. How many of you, what is the probability of this distribution being found difficult by this class? Okay. How many of you found it difficult? Nobody. How many of you did not find it difficult? Everybody's undecided.
Everybody's in between. Not easy, not
Difficult. We've given you some toys to play with. It's like those verbal kind of, quizzes that you have, no? You try things. Okay, difficult. Can't grasp the concept. Yeah, fair enough. Fair enough. Absolutely fair enough. Everything that is new will take time to, grasp. Okay, but he's also hopeful, but we'll get there in due time. Excellent. Okay, anybody else who found it difficult? Okay, honestly, how many of you tried it?
I tried it.
Okay, you did. Okay, Dr. Biju tried it. What about the rest? Did you try it? Both the
Sorry.
binomial? Okay, he got the answer also in the end. Okay, so I'm going to send you, this presentation. Okay, in a day or two. Let me just do some corrections. Okay, and please go through the presentation. Okay, you will kind of understand. Okay, see both these are used extensively in medical sciences. Okay, the only thing is that when you look at a situation, okay, and you want to look at it in terms of probability, how is it that you are going to model it? Okay, in what situation will you use a binomial, and in what situation would you use a Poisson? Right, in a Poisson it is mostly in terms of like adverse events or something in an interval of time, whereas in a binomial it is more like probability of success or failure. Okay, and then you find the probability of success. Okay, so you may have averages of a particular situation. Okay, but now you want to look at it at how does it apply to a particular experiment or a particular situation. Okay, so that is in terms of a binomial, whereas in a Poisson it is, as I said, it's usually it's like very rare, and it is based on the interval of time. Okay, so Poisson is also used, but it has to be time specific. Okay, there is always an interval that is relevant. Okay, and both are discrete because you are looking at a specific probability. Okay, yes, of course, anything that you study is going to help, right? If you do probability, you pick up a book on basic statistics, right? It will help. Only thing in a basic statistics we may not,
Madam,
I don't know how.
can you recommend any book if possible?
You want to do medical statistics? You
Yeah, I
want to
mean,
do
like understanding what you have said, properly. I mean, I want to understand the basics of it. So
okay.
that would help us. So any book which is talking about all these Poisson this thing and all those distribution, standard distribution, all those things.
Okay,
I mean,
so any book on biostatistics that you pick up will give you some idea.
any
Okay.
author which you can
So, for
suggest?
example, I am using something by Daniel Craig.
Daniel Craig.
Cross. Yeah, it is Daniel and Cross. Daniel and Cross.
Because Daniel Craig comes in the.
I know. Sorry. The moment, word association, Daniel Craig. No, it's Daniel and Cross.
Okay.
Okay. Couple of another two books are there which you can, for example, if you go to pdfdrive.net, okay, and you kind of search for a book on biostatistics, you will find some Indian authors. And if you go to Amazon also, there will be, relatively, decent books on biostatistics. So pick up anyone. Right. So at the end of the day, we are doing biostatistics. Right. There is really no difference between statistics and biostatistics, except maybe something in terms of survival and all, which we normally use. But the rest, by and large, any statistics book, they'll teach you the same stuff. Okay. The only thing that I'm trying to do is use more examples which are, medical related or something, so that you can kind of relate to it better. The rest is, right. But everybody has understood the calculator. You can, copy the calculator and, save it somewhere. Okay, so try it out, right? Think of those options, think of those situations. Okay, so Dr. Sunil, I think I'll hand over the thing to you, because I think you have another class, right? I'll leave, and I think you can carry on with your next stuff.
Thank you, Vinti. See you next
Okay.
Saturday.
Wish
Thank
you best of
you.
luck.
Yeah.
Yeah.
See you in the next session. Thank you
Yeah.
so much. Bye. Sunil sir, you want me to continue the recording or I can just leave?
No, I think we need not record this.